In this tutorial, we're just going to handle some chemistry practice questions. So, introduction to chemistry, we'll look at accuracy and precision, we'll look at significant figures, we'll look at determining the formula, we'll look at the oxidation state, we'll look at conversions, we'll look at again the oxidation numbers and all that. So then we'll look at combustion analysis, we'll look at formula again, basic stoichiometry and isotopes, percentage yield and whatnot. So question 1 is based on the accuracy and precision. Which data set has the best combination of accuracy and precision if the true value is 6.72 grams? What does that mean? So if the true value has been given, for you to determine the accuracy of a value, you would have to compare against the true value. So let's say if I know the length of a rope is 2 meters, the accuracy of somebody taking measurements is based on how close their value is going to be to that. For example, somebody measures to say 1.89 meters. So I can say they're accurate because they are close to that value. That is for accuracy. Now, precision, on the other hand, is based on comparison of values, several values that you take. So in this case, for example, we've been given 3 measurements. So if somebody can measure again, they get 1.8, again 1.83. You can see that these 3 values are closer to each other. So that is what we call precision. Okay? Closeness of several measurements. Comparison of a value against the original, that is accuracy. Now, precision can still occur even when the values are not accurate. By that I mean somebody measures 5.1, 5.2, 5.3. Of course, the measurements are precise, yes, but not accurate because they're not closer to the actual value. I believe that now differentiates the two. So the question is now asking us to look at the combination of both accuracy and precision in the data given. So for A, would you say these measurements are accurate? So I can agree yes, because they are closer to 6.7. That is 6.7, 6.7, 6.7. They are all closer to the true value. Now, not only are they closer to that true value, they are also closer to each other. So even before looking at the others, I feel the first one should be the correct answer, because the values are closer to that, making them accurate, and then they are closer to each other, making them precise. Now, as you check the second one, B, of course, the values are not as accurate as compared to the first one, because the actual measurement is 6.7. So these are far from 6.7. So not accurate. And then we can also say they are not precise because they are not very close to each other. But if I check the third one, they are also not close to each other. One of them is accurate because it's actually exact. Then D, this is, I can say that is accurate, but the values are not closer to each other. So these other two values are not accurate. So the first one qualifies to have the combination of the best accuracy and precision. How many significant figures are there in the value 8 by 10 to the power 8? So whenever you have a number given in the standard notation, don't focus on the power. So you look at this number 8.0. How many significant figures are there? So all zeros after a decimal point on the right hand side are significant. So making this value to be 2 significant figures. So if it was not decimal point, let's say just 8 times 10 to the power 8, it would be a single significant figure. Okay, that's the way you look at the significant figures in terms of that notation. But of course, in a case where you've got leading zeros like that, these are not significant. Okay. Correct formula of iron 3 oxide. So we have iron 3. Some of you know that we also have what we call iron 2. Okay. Iron 3. Yeah, iron 2. So in this case, we want to find the formula for iron 3 oxide. Oxygen has got an oxidation number of a 2 minus. So for us to find the formula, these will just exchange as. So the 2 will go there, the 3 will go there. So we have 3 Fe2O3, which matches up to which one? Which matches up to B. So B is the answer. A reagent that can be weighed easily and its mass truly represents the number of moles of a substance contained is called a reagent that can be weighed easily and its mass truly represents the number of moles of substance contained. So basically, without wasting much of the time, this is what we call a primary standard. A primary standard can easily be weighed and its mass truly represents the number of moles contained. Okay, so a primary standard is what we use now to create what we call a standard solution. So a standard solution is a solution of well-known concentration. So for example, under titration, you can use what we call a standard solution because you know its concentration. So a primary standard can easily be weighed and the number of moles can easily be determined is what is used in coming up with a standard solution. Of course, we know what a limiting reagent is, we know what an oxidizing agent is. Find the oxidation state of I in iodic acid. So of course, all these videos are available in full. If you want to learn about, for example, these basic calculations in details, from the second tutorial sheet, actually we've talked about it more in details. But I'll go straight to the point and answer the question. HiO3. So oxygen, the oxidation state is -2. For hydrogen, it's +1. So we just need to find for. Now, when there's no charge on the overall compound, the charge is taken to be 0. So for hydrogen, we only have 1. So I'll say 1. Iodine, I'll put X. And then we've got 3 oxygen atoms, each having a -2. So this should be able to give us a 0. 1 plus X minus 6 is equal to 0. X becomes 6 minus 1, giving us a +5. So that is the oxidation state of our iodine in this question. Convert 9.3 meters to micrometers. So you ought to understand what micro means. So micro means 10 to the power -6 meters. So whatever value you have multiplied by 10 to the power -6, that's what micro is. Just in case you also get to meet nano, when you see nanometer, it's 10 to the power -9. That's the easy way I think about this. So if I've got 9.3, I'm going to micrometers. I'm going to a smaller value. So I just have to multiply by 10 to the power 6. 10 to the power 6. So 9.3 times 10 to the power 6 is in micrometers. Okay. So that's the value. In other terms, what I'm trying to say is 1 meter is equivalent to 1 times 10 to the power 6 micrometers. The reason is simple. Because micro stands for 10 to the power -6. So if I want to take the right hand side back to meters, Where there's micro, if I put 10 to the power negative 6, it will cancel with this one, so giving me meters. So if you're moving from a bigger unit going to a smaller one, multiply by the positive. If you're going the other way around, you divide, or in other terms, multiply by a negative power. That's the way that works. So, by the way, I need to check the answers if it's there. So it's the C. It's C. The manufacture of sulfuric acid by the contact process can be presented as follows: sulfur, sulfur dioxide, SO3. So we need to give the correct sequence of oxidation number at each stage. So whenever you've got an element in its original state, just like sulfur, the oxidation state there is expected to just be a 0. Okay, so therefore A and D qualify to be the possible solutions. If I got the second one, sulfur dioxide, SO2, so I'll put X for sulfur. We've got 2 oxygen atoms, so I already told you oxygen is -2, so equated to 0 because of the fact that there is no charge on the compound unless otherwise. But according to what I'm saying there, but SO2, according to what I'm saying there is no charge. So I'm just trying to confirm it's supposed to be a charge or not. So there's no charge. So if there's no charge, we equate it to 0 like as it is. So therefore our X will be equal to +4. So already we have 0, +4. So making the A to be actually be the answer. So in an exam, that is already enough for you to end there. But for more confirmation, you can go up to the third one actually. So I'll put X for the sulfur, and then we've got 3 oxygen atoms. I'll put a -2 equal to 0. So already that tells you X is going to be +6, right? Yes. So that's enough. Of course, you can try take hydrogen to be +1, oxygen as well -2. So the answer is A. In which of the following changes is the nitrogen reduced? So you can look at reduction actually by observing the oxidation state of nitrogen in each state. So if I look at the first one, nitrogen initially, I'll take it as X plus hydrogen, it's 3, it's a positive, so it will just be 3. If I equate that to 0, for nitrogen I'll get a -3. So there it's -3. Now where it is combined with oxygen, I know that oxygen is a -2. So if it is to give me a 0, then nitrogen is supposed to be a +2. So to me, that is oxidation, because there's an increase in the oxidation state. So we already know that from NH3 from the previous question, it is -3. Now what about NO3? 3 negative. So NO3 negative, what does that mean? So NO3 means we've got like, how am I supposed to put it? So in this case, I'm trying to make sure what I have is right. So this 3 is supposed to be a subscript, and then the negative is like the charge. So taking that as a case, nitrogen will take it as X, and then we've got 3 oxygen atoms, and then the charge is -1. So X minus 6 is equal to -1. X becomes 6 minus 1, so +5. So that is also oxidation, that's an increase. Nitrogen in its original form it's 0. In NH3 we've already seen it's -3. So I can already observe that that's reduction. From 0 to -3 is reduction. Then finally the last one, so this having a charge is -3. In its original form it's 0, so that's increase. So reduction is C. Name the reaction given below. So if you look at this given reaction, we have to name it. So we need to make some observations with what's happening. So that's where we have our potassium. On the product side, it is connected to the nitrate. The nitrate initially was connected to barium. Okay, so this way of what I'm saying here is like there's an exchange. There's an exchange. Barium has attached to the I don't know if it's the chlorate or what, or something like that. Yeah, so in this case, this reaction is called double decomposition reaction. Now, double decomposition reaction is where they are swapping where you've got compounds swapping. They are called double decomposition reaction. So they can be classified as two. One is neutralization, the other one is precipitation. So precipitation is a case where there is a solid being formed. Okay? Meaning that these others will remain as spectator ions, but there is a solid that is formed as a salt. So in this case, this is a precipitation reaction because of that solid formed. Okay? The other, for neutralization, this is a case where you've got an acid reacting with a base. For example, sodium hydroxide and hydrochloric acid. That's an example of a neutralization reaction. Decomposition reaction, on the other hand, involves adding a compound, for example, sodium chloride, now breaking down. That is a decomposition reaction. Displacement reaction involves a more reactant, for example, usually metals, displacing another. I can think of an example of, let's say, lack of a better example, just to try to demonstrate. Let's say we had X, and then X was more reactant, is more reactant than sodium. So in terms of the product, you get to have X chloride, meaning that the sodium has been displaced by the more reactant metal. We are now on 10. On complete combustion, 0.246 grams of an organic compound gave 0.198 of carbon dioxide and 0.1014 of water. What is the ratio of carbon and hydrogen atoms in the compound? So the basic idea here is combustion. So we are having a certain compound. We assume it only had carbon and hydrogen as the question asks us. So that was being combusted in oxygen. Now, complete combustion implies carbon dioxide is produced. Of course, that has already been mentioned in the question because we are told give carbon dioxide and water. So under combustion analysis, we basically use the ratios of carbon in carbon dioxide and hydrogen in water. So for hydrogen, there are two atoms in the water molecule. So we use these ratios to help us get to find the mass of carbon and the mass of hydrogen respectively. So if you check your periodic table, you should be able to see that for your carbon is 12.01. So I'll quickly add on the bottom. For carbon dioxide, we'll have 12.01 as well, plus 2 multiplied by the 15.998 of our oxygen. So I'm getting 44.0096. All the same, the other side for hydrogen, we expect to have 1.008 now times 2. So 1.008 times 2, we have 2.016. On the bottom, the 2.016 plus the 15.998 of the oxygen. So we have 18.0158. So these are the ratios. Now we'll multiply against the given mass. So for water, we are told it's 0.1014. And then for the other part, for carbon dioxide, we are told 0.198. So what do we expect there? 2.016 divided by 18, that's for our water, multiplied by 0.1014. So the value I'm getting for as my mass of my hydrogen is 0.0113468. We need to move to the other side as quickly as possible. 12.01 divided by 44.0096 multiplied by 0.198. So here I'm getting 0.054033321. So these are the masses of carbon and hydrogen respectively. So don't forget, on the left we had carbon, there we had our hydrogen. So these are the masses. So at this point we are supposed to divide by their molar masses. So that is 12.01. Hydrogen, it's 1.008. So I'll begin with the carbon. So the number of moles that I'm getting for my carbon, I'll take about 6 significant figures. So I have 4.499. I think 4 are enough, times 10 to the power negative 3. So those are the number of moles. And then the other side, 0.011346684 divided by 1.008. So for my hydrogen, I'm getting a value of 0.0112. So 56 will give me just like 57. Okay, that's also moles. So we found the number of moles now of the two. So for us to find the ratio, we need to divide by the smallest. So since we only have two, the smaller one here is expected to be the one on the left. So divide by that. Of course, if you divide by itself, it will give you a 1. So I'll just go direct and divide into the other one. 4.499 times 10 to the power negative 3. So 0.011257 divided by 4.499 times 10 to the power negative 3. So here I'm getting a value of 2.5. So even if I was to consider 3 significant figures, I'll still get 2.50. And then here dividing by itself is expecting to give us what? A 1. So what we are seeing is carbon to hydrogen 1, 2.5. So we can't just say 1 to 3. So we can be wise by, we know 2.5 multiplied by 2 gives us a 5. So multiply by 2 so that we have 2H giving us a 5. If you can't see that directly as well, there's 2 other ways. You can multiply by 10 if you want to. So the 1 will give you 10, the H will give you the other part, the H will give you a 25, right? So 5 there is still 2, 5 there is still 5. So that's the ratio. A 35.3 gram of element M is reacted with nitrogen to produce 43.5 grams of the compound that. So take note, we have M reacting with nitrogen, which we know exists atomically to give us M that. So the information we've been told is the element M was weighing 35.3 grams. And then we've been told the compound that was produced was 43.5 grams. So if we've been given the mass of the compound and then the mass of one element, we can subtract the two to get the mass of the missing element. So that's how we're going to get the mass of our nitrogen. So after subtracting the two, the mass of nitrogen is 8.2. Now the question is asking us to find the molar mass of the element M, which is unknown in this case. So we've already found the missing mass of nitrogen. The other key important idea in the question is the ratio between M and nitrogen has been given. They are in the ratio of 3 to 2. So take advantage of that. Those are the more ratios. So we'll try to come up with a way of expressing the number of moles of these elements. So for M, the mass has been given in the question, so just say divided by its molar mass. Let's say its molar mass is Y. And then nitrogen, of course we know the molar mass is 14. Okay. Now what we're trying to say is the ratio between the number of moles of M and nitrogen should be able to be equal to 3 to 2. Why? Because that's a ratio. So I believe you know that instead of putting a ratio there, we can just put division. Okay. So what is on top, or what is on the left, is M. 2, 18.2, 8.2 over 14, that is denoting the nitrogen. Yeah, that's one way we can handle this question. So you know that actually dividing is just more like crossing and multiplying, right? So that will swap, so that I have multiplication. So 14 over 8.2. There I will now have 3 over 2, just. And then we can perform simple mathematics there. So 35.3 multiplied by 14 divided by 8.2. So of course it's across to multiply 3y will be equal to the value of calculated times 2 so that value multiplied by 2 divided by 3. So my value of y is equal to 40.18, so grams per mole. So that's the molar mass. So if you check a periodic table, it is actually sodium, not sodium, it's actually calcium, that has a molar mass of 40 grams per mole. Yeah, so we found the molar mass of the element, and then we've also named the element by just using the ratio there, and then of course by finding the difference to get the mass of our nitrogen. Question 12 is dealing with issue of finding the limiting reagent. So I'll try to solve it as fast as possible as I can. So this is our equation. So for any information, a limiting reagent is what finishes faster in that reaction, or what is not enough. So I'll write down the given information. So we've been told 1.90 grams of NH3 reacts with 4.96 grams of oxygen. So I'll direct you by using this method. So quickly we can find the molar mass of our ammonia. So we know nitrogen is 14 hydrogen is just like 1 approximately. So if we take that, we have like 17 grams per mole. Of course, use your periodic table to get the exact values of the molar masses. For oxygen, there we've got subscript of 2, so expected molar mass is just like 2 times 16, which is just like 32 grams per mole approximately. Okay, so I want to find the limiting reagent here. We found the molar masses, so first thing we want to do is find the number of moles. So find the number of moles by dividing the actual mass by the molar mass. So for ammonia, 1.9 divided by 17, so that gives me 0.1118 moles of ammonia. For oxygen, 4.96 divided by 32, so 0.155 moles of oxygen. Okay, so we're good. We just now need to find, so these are the actual number of moles that were available at the start of the experiment. Now we need to determine which one finished faster. So one way we can handle this is by getting any number of moles of our choice. So I'll go for the ammonia one. So okay, let me go for the oxygen one. This is the value of oxygen that we are given in the question. So it doesn't matter whatever you get. Now we'll compare our reactants. Our reactants, we've got ammonia and oxygen. Now these are in the ratio of 4 to 5. Now I've decided to get the number of moles of oxygen, which is 0.155. And then I'll assume I don't know the number of moles of ammonia, so that I cross and multiply using the ratios and see the number of moles of ammonia that are required by that number of moles of oxygen. So if I cross and multiply times 4 divided by 5, the value of x that I'm getting is 0.124 moles of ammonia. So those are the number of moles that are required by 0.155 moles of oxygen. So if you compare the required number of moles of ammonia against what was available, which one is bigger? So the 0.124 which is required is bigger than what was available. So in this case, ammonia wasn't enough, making it to be the limiting reagent. Okay. Alternatively, if we wanted, we could have used the number of moles of ammonia. I put 0.1118 there, and then I cross and multiply to find the value of y. 0.1118 times 5 divided by 4. So the value that I'm getting of y is 0.139. So by just looking at that value compared against what was available, which one is bigger? So what was available of oxygen is actually bigger than what is required. So therefore the oxygen was in excess. So limiting there is ammonia. We've dealt away with that already. The second question is asking us to determine how many grams of excess reactant had remained. So to save some time, don't forget that the number of moles of ammonia were 0.1118, if I'm not mistaken. So what's the number of moles? So why am I writing that? So the number of moles of a limiting reagent is what determines how much of the other reactant is going to be used up and how much of the products will be produced. So therefore, using the mole ratios, these are in the ratio of 4 to 5, so we can use that to find the number of moles of oxygen that had reacted. So if we cross and multiply, we'll put x there so that we do, assuming that we don't know the number of moles that are reacted of oxygen. So the value of x, so 5 times 0.1118 divided by 4. So the value of x is equal to 0.13975. So that is denoting the number of moles of what? Of oxygen. Now at this point, what do we know? We found the number of moles of oxygen that had reacted in what? In the reaction. So we can use the number of moles and actually the molar mass to find the mass that reacted. So we know that the oxygen exists atomically. So 2 times 15.998 15.998, so approximately that would give us 32 grams per mole. So using that molar mass and number of moles, we can find the mass. We know that mass is the product of the two. So times 0.13975. So the value I'm getting is 4.4719 grams. That's how much had reacted. So if this is how much had reacted by using the limiting reagent to determine it, and then in the question we are given how much was available, so we can subtract the two. So the value that had remained is 0.488 grams. The last one is asking us to determine how much of NO was formed. So they are in the ratio of 4 to 4. So that means they're in the ratio of 1 to 1. So the number of moles of the limiting reagent will be equivalent to the number of moles of what? That product. So no need of you using a variable x, it will still be the same. Now that we've got the same number of moles, all we just have to is look at NO and find its molar mass. So it's made up of nitrogen and oxygen. So if we add the two, 14 plus 15.9998, so that is our molar mass, 29.9998 grams per mole. So using that molar mass and the number of moles, we can find how many of the grams were formed. So how do you go about that? So that's going to be like a product of the two. So the mass that I'm getting is 3.354 grams. So that's how we handle question 12. Question 13 is very simple and straightforward. The isotopic mass of chlorine 17 and chlorine again are, so chlorine 35 and 37 are that respectively. The atomic mass is that. What is the isotopic percent composition of the two isotopes? So all this has already been covered in another video. You can learn about it more in detail. So the key idea here is we've got chlorine 35 and chlorine 37. Okay. So if we know the percentage of one, we'll be able to find the percentage of the other. So I'll just go direct. So for the chlorine 35, the 35 was just like a round off figure. So the actual value is that. So 34.968852. Okay, so we'll take it to be the percentage to be x, and then plus, then the other one, which is 36.965902, we'll take it to be the difference from 100, so 1 minus x. So we use 1 to denote our percentage, so that if we get the answer value of x, we just multiply by 100 to get the percentage value. So this should be equal to 35.453. So the argument there is the isotopic mass that you have multiplied by the mass percentage, or let me use even a different value. So the isotopic mass that you have multiplied by its percentage plus another isotopic mass multiplied by its percentage should be able to give you the relative atomic mass of that element. So that's what I'm trying to say there. So our goal here is to find the value of x. So what we're going to see is, I want you to be thinking very smart. So this is going to carry x. Again, if you multiply this by the negative x, it's also going to carry x. So just subtract directly. 34.968852 minus 36.965902. So the value I'm getting is negative 1.99705x plus, so this times 1 will just be a positive value. As it goes the other side, it will become a negative. So I have 35.453 minus 36.965902. If you don't understand, feel free to do it step by step. So negative 1.512902. So divide by the negative 1.99 both sides, so that we find the value of the x. So x is equal to 0.7576. So that's the value of x. Now do pay attention that x was denoting chlorine 35. So if I multiply it by 100, the percentage I'm getting is 75 point 76%. So that is for chlorine 35. So from 100, the value you're getting is for the other one. So for chlorine 37, the percentage is 24.24%. So that's basically how you handle question 13. And finally, the last one, we need to calculate the percentage yield of the reaction. So where we are told for 1.5 grams of tungsten, 7, yeah, that is 6 actually. So tungsten reacts with hydrogen to produce tungsten and water. So that's a balanced equation there. Is it balanced? No. So for the oxygens, we are not balanced. There we've got like 3. So I'll just put like a 3 there. It's now balanced. So the information we've been given is that we have 41.5 grams of the tungsten 6 oxide, and then react with excess hydrogen. So that tells us that tungsten is a limiting reagent. And then 9.5 milliliters of water was produced. So percentage yield tells us that we just need like to compare the actual, how much is produced in reality, over the expected, which is like the theoretical or experimental percentage based on the calculations you make. So the actual, in this case, the only thing that we've been given about the actual production is water. So therefore we need to find the theoretical yield of water using the mole ratios. So the only way we can handle this is, for the reactant we have to use the limiting reagent, which is the tungsten 6 oxide. So you would have to check your predict table so that we basically get to have the value of the molar mass. Yeah, so the molar mass of tungsten is 183.84. So plus 3 times approximately 16 of oxygen. So 183. So the value is, the molar mass is approximately 231.84 grams per mole. So finding the number of moles, the actual mass is supposed to be divided by the molar mass. So getting a value of 0.17903. These are like the number of moles. So if we compare that limiting reagent of ours with the water, they are in the ratio of 1 to 3. Ratio of 1 to 3. So meaning that per every mole of tungsten 6 oxide, there are 3 moles of water that are produced. So if we try to find the value of X, meaning that it's supposed to be times 3. So the value of X becomes 0.5371. So that's the number of moles of water that we expect to be produced after this number of moles of the tungsten 6 oxide has reacted with hydrogen gas. So after we have our number of moles, we know that water actually, its molar mass is known. So of course we can just do it. 15.998 plus 2 times 1.008, so it's 18.0158 grams per mole. So we have the molar mass, we've got the number of moles. We should be able to find the number of should be able to find the mass, that is, by multiplying. So after multiplying, I'm getting 9.676 grams of water. So what is the theoretical expected yield? Now in the actual question, we are told, we are given the volume and then we are given the density, the Reagent. So the density will allow us to find so if I just say 1 grams per milliliter, the milliliters will just like go away. So the 9.50 becomes grams as the actual yield. So that 9.5 over the theoretical times 100 is basically what will give us so that is like 98%. Okay, so the expected was 9.676, the actual was 9.5. So it's just a matter of you being able to work around understanding which one is the actual and being able to use your stoichiometry to be able to determine the theoretical yield. So if you need access to the third, the fourth story sheet solutions, the second story sheet solutions from stoichiometry, atomic structure, chemical bonding, and also the other topics, you can use the link in the description. visit our website www.transcendentinstitute.com, or you can WhatsApp the given number in the description.